Hello, my name is Roy Simpson. I'm an instructor of mathematics at Cosumnes River College in Sacramento, California. This lecture we're going to concentrate on solving small linear systems using algebra. And when I say small linear systems, I mean systems that are of linear equations that perhaps just have two linear equations and therefore two items we don't know, or two unknowns, two variables, like an x and a y, or a t and an r, or something like that. There are two actual acceptable methods for solving systems of linear equations. One would be the substitution method. The other would be known as commonly the elimination method, or less commonly as linear combinations. In this part, we're going to talk about the substitution method. Both methods have their uses, and you'll switch back and forth between the two. Often you'll use the elimination method, to be honest with you, but it's still very powerful to use the substitution method every once in a while. We'll start this off by kind of recalling some of the ideas from the previous lectures about what a system of equations actually is. A system of equations is just a collection of conditions that must be satisfied. For example, your household must earn at least $80,000, but at the same time, to stay within a certain tax bracket, you want to keep your salary or income less than $150,000. So that's two separate conditions, and both those would actually lead to two separate, well, those would be inequalities, but two separate equations for now, we'll just call those. Okay, and the solution to the system is essentially what satisfies all those conditions. And what will satisfy all those conditions graphically is their point of intersection. So if you had, let's say, two equations in a system and one graphed out to look like this, and the other one possibly graphed out to look like this, well, everything on the orange line here is a solution to the equation that generated that orange line. And everything on the blue line is a solution to the equation that generated the blue line. However, there's only one point that exists on both. That point right where they cross. That would be the common solution. And that common solution we often just call the solution to the system. Well, that's a great way to view it graphically, but there's something you should note about this algebraically as well. Note that at the common solution where these two equations meet, their x values are the same and their y values are the same. For an example, both graphs don't meet exactly at that blue point I just graphed in there. That might be x equals 1, y equals 2. Let's pretend. And at the same time, I could pick another point. Let's just say this orange point here. That point might be x equals 0, y equals 5. And you see that those two equations, while the orange one lands on that point, the blue one does not. However, this common solution, both equations happen to land and hit that point right there. I should probably do this in red. Okay, so let's pretend that point is 2, 3. That point, 2, 3, exists on both lines. In other words, that's a solution. When I let x equal 2 into both equations, y will be 3 for both equations. Now, I debated upon how to introduce the algebraic concept of solutions. I just decided to go ahead and start with an example and maybe justify as we go along. So here, let's go ahead and solve this system of equations. Notice you have two equations. I'll even label them equation 1 and equation 2. Right now, it's not necessary for us to do that, but it's always a good idea as we deal with systems of equations to label our equations. It helps out in the long run. In fact, maybe I'll adopt a different notation here right now. Let's go ahead and label these row 1 and row 2. So I'll say that this is a row, and I'll call that row 1, and I'll call this row 2. And what we'll do here is we'll notice that each equation has two variables, and they're both kind of in a weird format. We could write both of them solve both for y or solve both for x or whatever we want. What I'm going to show you is without justification. All it is me just kind of changing the form of one of the equations, and then I want you to notice something that happens. So the top equation I'm leaving alone for now. That's just still row 1. The bottom equation, I'm going to go ahead and add y to both sides. And when I do that, I will get 6x plus 1 is equal to y. That's what row 2 is. Now row 2 only changed in looks, but it really is the same row. All I did was move that y to the other side. What's important to note here is that I want these two equations, or the graphs of these two, to meet up. So let's ask ourselves a question. When will the graphs of these equations meet? Well, they'll meet at a point, basically an x, y value that they share in common. Well, so if I know that the y value is supposed to be 6x plus 1 and I want them to have the same y value, let's then say, okay, this is our y value, 6x plus 1. Let's take that and substitute that in for what we see in the other equation, the y value in the other equation. In fact, I should use a different color here to kind of really show you what's happening. So I'm taking that 6x plus 1, which is equal to y, and in the first equation where I see a y, I'll replace it with that 6x plus 1. So in other words, row 1, which I'll go ahead and write right here, row 1 is now 2x minus 4 is equal to 3. Instead of y, I'll replace that picture y with this picture 6x plus 1. So if you want to visualize it, all I'm basically doing is I'm grabbing this 6x plus 1 and I'm shifting it down and dropping it down into the spot for y. But unfortunately it's a mess when I do that, so I'm not going to do that. Okay. And I suppose I could make you even visualize it just by doing it this way. Actually, I could just rally it up this way, grab it, and put it in for the y value there. That's exactly what we did. Okay. And at this point, you have a single equation with one unknown. One equation with one unknown. And that's exactly what you want. You want one equation with one unknown, because that's typical for all the equations we've solved thus far in mathematics. So let's clean up this equation. The left-hand side is just 2x minus 4. The right-hand side, I shall distribute the 3 to each of these terms inside the parentheses. That gives me 18x plus 3. And from this point forward, I just subtract 2x from both sides. Go ahead and just write it down here so you can see it happening. I get a beautiful negative 4 is equal to 16x plus 3. And now I shall subtract 3 from both sides. And I get a beautiful 16x is equal to negative 7. We're not done, of course. I'd like to know what the x value for the point they meet is. So I'll divide both sides by 16, and I find out that x is a negative 7/16. That right there is one of the coordinates for the solution. I know that they meet when x is a negative 7/16. Now remember, originally up here we had 6x plus 1 sitting right here, and now that I know what x is, I can find out what y is. So I'll just make a little note here. I'll say plug this in, and you can actually choose whichever equation. You can plug it into either the first equation or the second equation, but I'm going to plug this in to find y. And since I want to find the value of y, I already know y is equal to some value of x here. So let's go ahead and plug it in the second row. So I'll take row 2 here. I have y is equal to 6 times, well, it was x. We're going to replace it in a moment. plus 1. The x is a negative 7/16. So when you multiply this through, you'll see first of all that 6, let me do a cancellation trick here. I have to also change pen sizes. 6 goes into 16 three times, or I'm sorry, 2 goes into 6 three times, 2 goes into 16 8 times, and then that'll give us a negative 21 over 8 plus 1. And that 1 is just 8 over 8. So when you simplify this fraction, or this summation, let's see, negative 21 plus 8, I think that's a negative 13/8. Okay. So this tells me that when x is a negative 7/16, y is a negative 13/8. Write that down. And that happens to be where they meet. Not the best looking point in the world, but it is where they meet. And actually, if you were to graph this out, you'll see that that is technically where they meet. That's the exact value. Let's go ahead and graph this out. Now, to graph this by hand, we're likely to make mistakes. So instead of graphing this by hand, I'll go ahead and bring up a handy dandy graphing calculator here. And remember, to graph on a graphing calculator, if you don't have a graphing calculator, that's fine. But if you wanted to graph using a graphing calculator, you have to solve both equations for y. I'll just pretend as though I already have. So the first equation, if I solve the first equation for y, I would get 2/3 x minus 4/3. The second equation is just 6x plus 1. And I'm just doing this so you can kind of see where they meet. Now remember, if I hit graph, it might not graph on my window. It actually is here. And you can see they meet somewhere in this third quadrant. In fact, I could zoom in. Let me just show you a feature of a graphing calculator here. A lot of different ways you can zoom in to a graph on a graphing calculator. I'm going to choose the first one. This was always my favorite when I was a student, the zoom box. Select it. Nothing seems to happen, but if I hit the left arrow, you'll see I sort of have a cursor there. So if I just bring my cursor down and hit enter, it starts on upper left hand corner of a box. You'll see it when I go to the right and then go down, you'll see the box kind of open up. It's making a zoom box for me. Once I'm satisfied with what I want to zoom into, I'll hit enter and you'll see I've zoomed into that area. Still kind of ridiculously difficult to find out where they meet. I'll use my arrow keys to kind of get there. This says about negative 0.44 for the x value and a negative 1.6 for the y value. Again, if you're using a graphing calculator, you can actually calculate their intersection by just hitting second. Notice the up arrow for the second button. And there's a calculate menu right up along the upper set of buttons, which is your graphing menu. So if you hit the second button, I want to hit the trace button to access the calculate menu. There's a lot of different little options here, but the one I want is to find out where they intersect. So I'll select option 5. It'll say, hey, is this your first curve? I'll say sure, hit enter. It'll say, hey, is that your second curve? I'll say sure, hit enter. And then it says, hey, could you get pretty close to it? So I'll just get close and hit enter. It'll calculate it out, and this is what it gets, negative 0.4375 and negative 1.625. Now let's look at our x and y values that we calculated. And negative 7/16, so let me just hop out of this. A negative 7/16 is negative 0.4375, which is exactly what they told us the x value was. And then again, a negative 13/8 is negative 1.625. So that verifies to me that we're correct. Now, of course, I'm not going to just stop here and pretend we're done. I would like to get a little more practice on this. So let's go ahead and do another problem. So in this case, I just wrote up a system really quickly that has fractions in it. And this is a very interesting system because just because of the way it looks. It has a bunch of fractions. It kind of looks intimidating to students. I'm going to go ahead and call this first equation row 1 and the second equation row 2. And again, I'm doing that for future use, actually. And one thing I want to remind you is that when you have an equation like A equals B, you can always multiply both sides of that equation by any number you want as long as it's not 0. So in other words, you have this teeter-totter. That's what an equation is, right? It's like a seesaw or teeter-totter. Right now, both sides are equal weight. Well, if I add 5 times the amount of weight to the right-hand side, I better add 5 times the amount of weight to the left-hand side. In other words, you can multiply both sides, or if you multiply one side by a number, you have to multiply the other side by the same number. So let me illustrate that here by just saying if I multiply the right-hand side by a number c, I have to multiply the left-hand side by the same number c. Well, what does that have to do with this problem? When I see fractions in equations, I immediately say to myself, I'd like to get rid of those. I hate fractions, so I try to find the LCDs. In this first equation here, the row 1, the LCD for the group of fractions there is 6. Each of those denominators divides nicely into 6. So what I'm going to do is multiply both sides by 6. I'll have students that will swear up now, I have to get common denominators and get all the fractions to have 6 in denominator. No, you don't have to do that. You're wasting your time doing that. I'll just tell you that you're absolutely wasting your time. The bottom, actually they all have the same denominator, but I'm still going to do the same thing. The bottom one has an LCD of 4. So I'll multiply both sides by 4. When you do this, obviously the left-hand sides are pretty easy. 2 goes into 6 3 times. 4 actually goes into 4 once, so they cancel nicely. So row 1 ends up looking like 3m equals, and row 2 ends up looking like m equals. And as far as the right-hand sides, I'll distribute, for the first equation, the 6 through. I'll only do it slowly this one time. Usually I don't like to take my time doing this, but first equation, you'll have 7/6 times 6 minus p over 3 times 6. Second equation, you'll have 3/4 times 4 minus p over 4 times 4. And usually, like I said, I do not like to waste my time doing that, but it's to illustrate something. 6 goes into 6 very nicely, and 3 goes into 6 twice. 4 goes into 4, 4 goes into 4. And when you rewrite this system down here, you get this beautiful 3m is equal to 7 minus 2p. Don't forget that that's 2 times p there. And down the second equation, you get m is equal to 3 minus p. Still row 1 and row 2 here. Okay. But look how nice multiplying both equations by the LCD. Look how nice that looks now, because you get this beautiful system of equations with no fractions anymore. And in fact, this one is already kind of almost done for us, because it's already telling me, listen, we want to know when these two are equal. Well, when they're equal, their m values are the same. So in other words, this value of m should be the same as the value of m in the first equation. So what I could do is I could take this 3 minus p, grab it, and substitute that in for m into the top equation there. Right? Because I know that m is just 3 minus p, so wherever I see an m in the top equation, I'll replace it. So row 1 will now be 3 times, instead of m, it'll be this picture here, 3 minus p. And the right-hand side I'll just rewrite as 7 minus 2p. Let me go ahead and clean that equation up. That's just 9 minus 3p. Is equal to 7 minus 2p. I will go ahead and add 3p to both sides. Add 3p, add 3p. And The left-hand side will just be left with 9. The right-hand side will be 7 plus p. Now I'll go ahead and subtract 7 from both sides. Normally I wouldn't show all this work, but why not? And we get that p is equal to 2. P is equal to 2. Well, now that I know what P is, it's very quick to find out what M is, because look at row 2 here. I could plug that value of P into any of the previous equations. I could plug it in to this first equation or the second equation or these versions up here. But really, look how nice this equation is. I have that M is equal to 3 minus that value of P, which is just 2. That's a very fast calculation, right? M is just equal to 1. So this tells me that M is 1 and P is 2. That's where they meet, when M is 1 and P is 2. That's solving a system using what's called the substitution method. Okay, so maybe I should have written that down. I'll go ahead and do that. So I just quickly jotted substitution method down for solving systems here. The first major step is to isolate a variable in one of the equations. And it doesn't really matter which variable. Try to isolate one that's near to already being isolated or is very easy to isolate. Okay, so each choice I made in the previous 2 examples, if you rewind, you'll see I chose to isolate for a variable that was extremely easy to isolate. Okay, after you do that, you take that value, let's say you isolated for x, so you have x equals some junk. You substitute that junk into the other equation for that value of x. Okay, so that's the substitution part. At that point, you'll have one equation with one variable. That's very easy to solve for, so you just go ahead and solve that equation. That's step 3. And finally, once you find out what that variable is equal to, that numeric value, could be 3, 10, 1/3, whatever, then you take that value, substitute that into any of your previous equations to find out what the value is for the remaining variable. If you rewind this video, you'll see that's exactly what we did. We isolated a variable, substitute that into the other equation, solved, and then took that answer and substituted it in to find the remaining variable. The whole point of systems of equations, a lot of people don't realize this, I think, when they first learn them. The whole point of solving systems of equations is that they really dominate all of mathematics, engineering, physics, anything like that, because anything in real life is filled with constraints. You just have conditions upon conditions upon conditions. And so each condition, each constraint creates an equation. So you have a bunch of equations that have to be satisfied. And you can kind of think of it in language. Some people have this list of things that they look for in a mate. Oh, they have to be funny, and they have to be intelligent, and whatever it is. Each one of these is a constraint. So you can think of each one of those as a condition. And the more conditions you have, the harder it is to find a solution. So there's just as in real life, the more rules that you have for finding a mate, the harder it is for you to find that mate. Okay? So don't make 1,000 rules. All right. Let's try an application. This kind of application is a very famous style of application in most math courses. It's called a mixture problem. I tried to find the more difficult mixture problems to do so that you could see that no matter how challenging they are, you can actually do them using a very simple, straightforward process. And I even write out A, B, C, D, little steps along the way. So let's read this out. Some guy needs 40 pounds of a silver alloy to finish a collection of jewelry. A silver alloy is basically a mixture of silver and other metals. Okay, and it's 48% pure silver is what his alloy is. That's what he needs. 40 pounds of 48% silver alloy. How many pounds of a 45% silver alloy should he melt with 60% silver alloy to obtain the alloy that he needs? So the idea is that he has 2 kinds of alloy already, a 45% mix and a 60% mix, and he needs to either water down the 60% to get it down to a 48% mix, or he needs to thicken up the 45% mix to make it a 48% mix. Whenever you're doing a word problem. Remember way back when, if you've watched through all my lectures in the past, you know that I have a process to problem solve. It's a very simple process. Well, I say very simple. It looks like a lot of steps, but the idea is the first one's just read, right? You read the problem. If you don't read the problem, you get nowhere. Second thing you need to do is understand what's going on. Physically, what's the situation? Try to imagine what's going on. That's a kind of an important step. Well, we've read this, we understand what's going on. Then you label unknowns. Here we have a couple things we don't know. So let's go ahead and go through this. We've read the problem. We understand what's going on. I would recommend drawing the situation. People tend to love tables. You know, they like to build a little table for a situation like this. I really don't like tables, actually. I like to draw pictures. So what I'm going to do is first I'm going to label my unknowns, and then I'm going to draw a picture. So let's let, and that's a very important word when you label unknowns. Let x equal, let's see, things what we need to know. Let's see, how many pounds of 45% should he melt with a 60%? Okay, so we need to know, actually, there's two things we don't know here. We don't know how many pounds of 45% silver alloy he has, and I also don't know how many pounds of 60%. So let x equal amount of 45%, I'm sorry, alloy. And we'll let y equal the amount of 60% alloy. Again, the silver alloy. So those are two things we don't know. I happen to know how much he wants in the end, so I'm not going to give a variable for that because it's not variable. It's a constant. We know he needs 40 pounds in the end. And so we need to write equations for these. Now, you could easily just read this and most people would be able to figure out that, well, the amount of the 45% plus the amount of the 60%, when we mix them together, should become 40 pounds. We should have 45 pounds in the end. So most people would know that initially one of our equations will be x plus y is equal to 40. But I'm not going to write it that way first. I'm going to draw a picture so you can see. I have a vat. This is my vat, a cylinder or a bucket or whatever you want to call it. Okay. But I have a vat of 45% silver alloy. So just like you would see like in a store, a can of orange juice or whatever, I want to label this as 45% so that we know when we reach on the shelf that that's 45% silver alloy. And usually they have a weight on this can. I'll write the weight below it. We don't know how many pounds, so we said that was X pounds of that. We also have another can on the shelf. By the way, this works for mixing peanuts, and it works for mixing a bunch of different things, people, whatever it is, okay? Our other can is a 60% alloy, and we don't know how many pounds. We said we have Y pounds of that. And we'll have a final mix. I'll write the word mix above it. We will mix that to create a final can. And that one, we know we want that to be a 48% mix. And we need 40 pounds here. Just by looking at this picture, I know if you can imagine mixing these two cans together, you're basically adding them together. Okay, so you're kind of dumping both of these into this mix. So you're going to take these, grab them, and dump them into there. So you're going to add them up and dump them in. Now, this, I actually have my equations staring at me right now. If you look at this, don't think that 45 plus 60 is equal to 48. That math didn't work out, did it? So that is not what's staring at you. Right now, what's staring at you, the easiest one is that the x plus the y is equal to 40. So x plus the y is equal to 40. That's just looking at these things down at the bottom. I'll highlight them. X plus y is equal to 40. Let me highlight the equals and the pluses too. And finally, we need another equation because we have two things we don't know. We need two equations. So the other one I can do is say, well, wait a second, 45% of that x is going to be pure silver. So I could say 45%, or in other words 0.45x, plus 60% of that y, so 0.60y, should equal 48% of that 40 pounds. Now, what did I do? I basically just multiplied the 45% times x and the 60% times y and the 48% by 40. What does this represent? It represents the amount of pure silver. If we want 48% of this 40 pounds to be pure silver, well, you could find out the amount of pure silver by just taking 48% of 40, and that'll tell you have roughly about 20 pounds of pure silver there. So if I'm going to mix these two things up and throw them in there, they better have roughly about 20 pounds of silver in there. So I need to know that 45% of this first canister plus 60% of the second canister will sum up to that 20 pounds of pure silver. So let's go ahead. I'm going to have to open a new page to do this, but let's go ahead and write this system out nice and clean. And we'll go ahead and call that row 1, row 2. Before I even get started, I will let you know that I do not like having a bunch of decimals in a problem. So I'll do two things. One, I'll just go ahead and rewrite that top row as x plus y is equal to 40. But the bottom row here, I'm just going to multiply it by 100. So I get 45x plus 60y is equal to 48 times 40. So I multiplied each of the coefficients here by 100. And now I also should probably multiply 48 by 40. And that will be 1920. So let me just go ahead and erase this and call this 1920. All right. Now I'd like to solve this. Well, remember the substitution method says pick a variable and solve for it. So look at both these equations. The variable that's probably the easiest to solve for is either x or y in the top equation. And I'm just going to solve for y in that top equation. So in that top equation, I'll rewrite it as y equals 40 minus x. So I just subtracted x from both sides. Now that I know what y is, I will take that value of y, which is 40 minus x, and I'll plug it in to y in the other equation. So my row 2, my second equation, now becomes 45x plus 60 times y, which we now know is 40 minus x. And it's all supposed to equal 1920. Now I can easily solve this. It'll be 45x plus, I think that's about 2400, minus 60x is equal to 1920. Let's see, 45x minus 60x is a negative 15x, and I'll subtract 2400 from both sides while I'm at it to get negative 480. And now I'll divide both sides by negative 15, and that one I'm going to go ahead and bring in a calculator really quickly and just do 480 divided by 15. The negatives will cancel, so that's not a big concern. Move this off to the side. I'll get x equals 32. So I happen to know that x is 32. Now remember, once you're done finding out what one of the variables is, you can find out the other variable, the value of it, by plugging that value of x into any of your previous equations. Pick an easy one. For example, this one right here. It usually is this one that you use for the substitution. That's the easiest one. So I happen to know that y is equal to 40 minus x. And I know that x is 32, so y must be 8. Now that I know that x is 32 and y is 8, go back to the original problem. I know I labeled my unknowns, I wrote equations, I related and solved. Let me state the conclusion. X is 32, which means we need 32 pounds of 45% alloy and 8 pounds of the 60%. Now do a little logic check here. You only want to go up to a 48% mix. Well, most of that is going to be at 45%. You're just going to thicken it up a little bit. You don't need a ton of that 60% mix to thicken that up. So that makes sense that most of it, the bulk of it is a 45% mix. Okay. Now I didn't technically follow my little steps here, A, B, C's, because I kind of do that as I go through my method. Choose variables, write one equation about the amount of alloy, write a second equation about the amount of silver, which is the second equation down here. And then solve. So I technically go through and do that all at once. All mixture problems, well, not all, but most mixture problems can be done using a picture like this, by the way. They're really convenient. Okay. I know most people like the table, though, but just letting you know that this is a great tactic as well.